how to catch an exception that's thrown by code you didn't write so that you can react to that code telling you that you've made a really fundamental error. You've seen how to add throw statements to your own code so that you can tell folks who call you, hey, you've made a really fundamental error. That's almost the entire story of exceptions. The part that I sort of flagged to you earlier that we needed to revisit, unwinding the stack. This is what happens when an exception gets thrown. As you've seen, the code after the throw does not execute. If the throw is actually inside a try, which almost never happens, control goes out of the try, everything left in the try is skipped in terms of execution, and in addition, any locally scoped variables that you declared inside that try block go out of scope, which generally means their lifetime ends, their destructors goes off, and they are cleaned up from what we call the stack. Usually, you don't have try, if something throw whatever, catch, because you could just have your if. You usually have the throw a couple levels down in some function that you called. So for example, we had the throw in the constructor of a person object. Vector had the throw in the at function, or in code called by the at function. So when that happens, the function that you're throwing from, that stops right there. Everything that was declared locally to that function goes out of scope, and control goes to the line that called the function. If the line that called the function was in a try, then we have the stuff I just told you about. Everything local to the try goes out of scope. If it wasn't in a try, then that function is all over and everything local to that function goes out of scope and control goes back to the line it was called from, and so forth all the way up. Now, if you get all the way out of main, that's when you get that dialogue that you saw in our very first demo when we did not have a try or a catch. At that point, the application's over. If I wasn't running under the debugger, you'd get that problem that says, whatever.exe has encountered a problem. Do you want to tell Microsoft about it? All that. It's over. Life is more interesting if we stay in the catch, because that's when memory management comes into play. If some of the lines that were skipped are lines that do cleanup for you, whether it's closing files, whether it's deleting memory that you allocated on the free store, whether it's letting go of locks or database connections, this kind of cleanup code may be what got skipped when the exception got thrown. That's where unwinding the stack becomes important, because it can actually help you solve this problem. To demonstrate the lifetime issues associated with unwinding the stack, I've created and added to this project a class called noise. Noise just holds a string known as sound I make, but the constructor and destructor tell us that they're running. So someone's constructing a noise with this sound and someone's destructing a noise with this sound. I've added some lines to the main that construct a noise outside the try and a noise inside the try. I've also added a line here inside person that constructs a noise inside the person constructor. When the constructor ends normally, this noise would go out of scope because it's local to the function. As you'll shortly see, even when the constructor doesn't end normally, that noise still goes out of scope. In here, what I expect to see is that this noise will go out of scope when the exception is thrown because it's local to the try, and that this noise will not. Let's see if my expectations match what happens. Here's how it went. First, we constructed the beep, bloop, and speaking noises in that order. Let's take a look at the code again. Here's beep, bloop, and speaking is inside the person. Then when the exception was thrown, the speaking was destructed because it was inside the constructor and local to that constructor scope. And bloop was also destructed. It was local here to this try. But you'll see that beep has not been destructed. It was allocated on the stack before the try. So the exception being thrown has had no impact on the lifetime of that object. Knowing that this object has had its destructor go off and it's been cleaned up is actually super important. It means that we don't need to check in our catch about whether or not we need to deal with that object. It was local to the try, exception's been thrown, it's been cleaned up. The number one reason why unwinding the stack matters is actually because of things that aren't on the stack. Things like memory allocated on the free store. When we talked about manual memory management, we talked about the idiom resource acquisition is initialization. This refers to the idea that when you acquire a resource, like getting some memory off the free store or opening a file or getting a database connection, what you really should be doing is initializing an object. And then the destructor of that object can release the memory, close the file, release the lock, whatever it is that you need to do. We'll use memory as our example, but this logic applies to any resource whatsoever. Take a look at the two pieces of code I'm about to show you. Here, inside a try block, we're allocating something on the free store with new. And I'm using the C++11 feature auto because I don't really care what this is. It's an X pointer, right, with a star, because that's what new X will return. Then some bad things happen, and then at the end of the block, I'm going to delete the pointer. So it's manual memory management. In this circumstance, if there's an exception thrown by the code in risky stuff, the flow of control will go to the catch block, and we will not execute the line that deletes X. This would be a memory leak. You could put delete X in the catch. Two problems with that. One, it's repetitive. Two, if my try block was a little more complicated than what you're seeing here, maybe I don't need to delete X. Maybe we deleted X and then we did some different risky stuff, and it's the deleting of some Y that's getting skipped. You need to have all kinds of if in your, if this is null, and it's nasty. Really is. Some languages cope with this a different way. But in C++, the way to cope with this is not to do manual memory management or anything else manually, but to use resource acquisition is initialization, to create an object on the stack whose destructor will do the cleanup for you. So whether we leave the try block in the normal way, by just reaching the brace bracket and carrying on with our lives, or whether it's because exceptions are thrown, either way there's going to be a destructor going off, and the destructor is going to tidy up. So take a look at this piece of code. Now we're using shared pointers. Make shared, I hope you remember, returns a shared pointer to, in this case, X. And I'm using auto because I don't feel like typing out shared pointer to X. I don't need to hand delete X at the end of my try block because the X now is not a pointer that can have delete called on it. It's a local object allocated, we like to say, on the stack, whose destructor will deal with the free store memory as appropriate. If risky stuff made copies of X, passed it around to other functions that held on to it, and so on, you might not even want to delete X when you get out of here because someone else may still be using it. That's the joy of a smart pointer, a shared pointer. But if you are done with it, it will clean itself up. Now the great stuff is if risky stuff throws an exception, we go out of scope. We unwind the stack. And as part of unwinding the stack, the destructor for X will go off, and that will clean up the memory. So there's no chance of a memory leak. When I covered shared pointers, I said this is even more useful when exceptions are in play. And now I think you can see why, because otherwise that line you skipped, you might have to repeat it, generally blah. Now, I know that in some other languages, there's a keyword like finally to handle this repeated cleanup. There is no finally in C++. And as you can see, there isn't a need for a finally in C++. If you use this idiom correctly, allocating local stack objects whose destructors will do your cleanup, you don't need a finally. The destructors will do all that work for you. Less code to write and test, and it's also more elegant, which counts for me. It's good performance benefits as well. So now do you think exceptions are the greatest feature ever, saving you all the trouble of checking a big long chain of return values and guaranteeing that nobody can forget and fitting even into functions whose return values are already used? They're great, but it is important to remember that they cost computationally. It takes time to be an exception user. Now, not to set up the try and the catch. If the exception's never thrown, there is a small computational cost when you enter the try to sort of notice where we need to come back to if there's trouble. If you actually throw an exception and catch it, that uses up way more time than just having an if to test a condition. That's a great reason why they're better for things that happen much less often, and especially for things that are really catastrophic if somebody forgets to check for them. Don't go and use exceptions for data entry validation like somebody entering a ridiculous date. You're right there. You test it, you give them an error message, it's all in one place. Where you use them is in these deep calling hierarchies. So a function calls a function, which calls a function, which calls a function, and way down, 7 or 8 layers down, we detect trouble in some manner. And if that function returns false, then the guy one up the hierarchy needs to say, if he returned false, don't do any more processing because we don't have anything to process or deal with. Maybe do some cleanup, return false myself, someone else has to. And there's a computational cost to that, to all that ifing. If there are no try catches anywhere in this big long hierarchy, if there's a try, let's say in A, but B, C, D, E, F don't have any try or catch in them, then what's going to happen when the exception is finally thrown all the way down is there'll be stack unwinding, so local variables will all be destructed all the way up into the try, and then control will go to that appropriate catch block. Your code is neater, and it's actually faster because you're not having those ifs all the thousands of times that everything ran smoothly, and you only have a computational cost when trouble happens. For things like, wow, your password was great 5 minutes ago, but your network credentials just became bad because your password's expired, or we had the network when you browsed, but the network has stopped and fallen down, or that file has disappeared, the hard drive's full, we're out of memory. These are really rare occurrences, and those are the best ones to use exceptions for. So you've got the combination of a really deep calling hierarchy and a really rare occurrence, it's screaming for exceptions. When you have a very, very shallow calling hierarchy, like one function deep, and a dirt common problem like users typing bad values, that's a bad case for exceptions. Knowing about exceptions makes you a better developer. You don't want to overuse them, you certainly don't want to underuse them, and when you're using code written by someone else that used them, you need to understand the consequences of that for you. The rule of thumb, exceptions are for unusual, of course, exceptional situations. That's what they really handle well. So your try sets up some context, knowing something might go wrong starting here, and I am the place that knows how to deal with it, no matter how far down the calling chain it happens. Somewhere way down the calling chain, you run into trouble. The throw is capturing information. Now, the standard exceptions we use, the only information pretty much that it captures is the string, which might as well be boy or stupid, and the type, like out of range or invalid argument. You can make your own exceptions that capture more information. It would be really helpful to know, look, you tried to access element 99 and this vector is only this long, then you can write an exception class that carries more information around if you want. At the instance of the throw, that information is gathered up and given to the location that can solve it, which is to say the appropriate catch block that was paired with the original try. The catch blocks associated with your try are kind of offered the exception in turn. So there might be a catch for ints, a catch for strings, a catch for invalid argument, a catch for out of range, and so on. You can also take advantage of polymorphism by catching an instance of a base class that will match any derived class. So if you want to catch the derived or more specific ones first, make sure their catch blocks are before and finish up with the more general catch block that catches, let's say, exception. And remember to catch by reference so you don't get object slicing and you don't lose the type, which in the case of the exceptions in the standard library is really the only information that you have, so it would really be a shame to waste it. Now remember about unwinding the stack, but everything between the throw and the catch, anything that was locally scoped along that way will be cleaned up. Its destructor will run. If it's just a solid object sitting on the stack, that's great, you're done, the destructor went off. If you're wrapping up some sort of resource like an open file or memory on the free store, it's also great that the destructor will run and clean it up for you. You know, if you have a vector of person objects, the vector's destructor will clean up all the individual person objects that were inside the vector. That resource acquisition is initialization really is sort of a clean lifestyle for managing these things in a world where there is exceptions, multiple returns, lots of ways out of functions. You're not always sure where the end is. Don't worry about it. When we leave this function for whatever reason, the destructors will go off. And as you've seen, that exception class in the standard library, super useful. You can expect to be catching things that derive from it, and you may also throw them, if you wish, in your own code and then catch them elsewhere in your code. Take advantage of the work that's been put into creating that hierarchy for you.